everyone. This is a programming practice session for linear regression. In this session, so we're gonna see some of toy example using linear models, and also this example gonna include statistical tests of coefficients. These concepts are already covered from the excuse me, previous sessions. Okay, so let's move to the actual programming part. Okay, so as always, in this second course of the machine learning course, especially for the supervised learning. So here we also want to use this the R programming language. Okay, so for the basic use of this the R and R Studio, or the basic grammar of this R, please see the first course of my section of the first course, the mathematical fundamentals for data science. Okay, so I assume that you are already a bit familiar with the use of the R. Okay, so in this example, so we're gonna start from some simulated data, which is the randomly generated, the artificially generated data. And because this artificially generated data is totally random, so whenever we regenerate the data, we're gonna see the different data. So in order to prevent those the variability of this the random generation, before we start, we're gonna set the random seed first. So that the I and you can see the same result. And the way to the set random seed in R is using setSeed command. SetSeed, then you can provide any number. Let's say here we're gonna do 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. Then this 1, 2, 3, 4, 5, 6, 7, 8, 9, that is a random seed, and the next number that randomly generated is always fixed. Okay? Then you and I can have the same result. And first we set the number of samples. Then let's say that's a 20. So n is a 20. Then first we randomly generate the x1 random variable, some random sample values of x1 from the normal distribution using our norm. Then we're gonna use the n, generate n numbers from the distribution of normal distribution with the mean 1 and standard and variance is 2. Okay. Then we have x1. If we see the x1, it generated 20 random numbers. Okay. Similarly, we can generate x2 with our norm and same number. And this one has the zero mean, and let's say standard deviation is 1. Okay. And x3 is another random number with n random numbers. In this case, it has the -1 of mean, and standard deviation is 1. Okay, here we have x1, x2, and x3. So from this x1, x2, x3, we build an output variable y. So this y is the linear combination of x1, x2, and x3. So, and it has the interceptor term 3 plus. So this 3 is correspond to the beta 0 in the linear model. Okay, and it is combined by the y is combined from 2 times of x1 plus and 0 times of x2. Here, the coefficient of x2 is set as 0. That means x2 doesn't contribute to the y. So this model, so y has no correlation with x2. And plus, then we have 5 times of x3. Okay. Okay, so this is totally model itself. However, in the real world, we always have some observation noise, which is the irreducible error. That part can be modeled by another random number, random samples from normal distribution. Usually, that normal distribution has the mean 0 and certain standard deviation, but here we're gonna use the standard normal distribution. So R known and same number, and we're gonna generate n number and from mean 0 and standard deviation 1. Okay, this is why. Here, we generate the x1, x2, and x3, and y. Okay, so our goal is regress y, regress this y using 3 random variables x1 and x2 and x3. Then first goal is to find out the coefficient. The second goal is to test whether this is the real whether the estimated coefficients are truly non-zero or not. So this is a statistical test. Good thing is here because this is a simulated data, we already know the true betas, true coefficient. So then we can compare, right? Okay, so before we actually move to the real analysis, almost at all the time, if you have the data, if you look at the data at the first time, the first thing you need to do is the exploratory data analysis or EDA, exploratory data analysis or EDA. Okay, which is so EDA means that we just want to see how data looks like. Okay, so in order to do that, so let's combine this y and x1 to 3 as the one data frame using the data frame function. So we combine as a one data x, y, and x1 and x2 and x3. Then D is similar to the matrix. So if we see the first 10 samples of D, then it looks like this. So here is y's value and x1, x2, x corresponding x1, x2, x3. And for the EDA, the best thing for the EDA is looking at the scatter plot. That means how x and y's are distributed. That means what's so it's just a visualization for the relationship between two variables. Because we have in total 4 variables, okay, so we want to see every pairs of this every pairs. So we want to see the relations between the every pairs. So that part can be easily done by pairs command. So if you do the pairs with this data distribution D, oops, there's an error comes out, but okay, so anyway, it works. So it actually shows such a plot. So the way to see this plot is basically show the scatter plot. So okay, let's see this scatter plot. This scatter plot is this horizontal axis is x1 and this particular axis is y, right? Here's y and x1. Then it shows you the scatter plot between these two, y and x1. Then the pointer looks like this. And this one is between y and x2. Okay? And This one is, this scatter plot shows y and x3. And this one is scatter plot between x1 and x2. Okay, in total there is 20 points. So from this, the visualization of this data, so first thing is we can see is, okay, y has somewhat the linear, somewhat correlated with x1 and x3, but not much correlation with x2. So that's very obvious because we designed the data in such a way. Okay, so uh, okay, so then if you want to see this numerically, we can measure the simple measure of the correlations. So you know what's the correlation. So this correlation is means the correlation coefficients. Okay, please refer the other class. So the fundamental mathematical fundamental class. Then correlation of the D. Oh, it's not DF. Okay, D. Then it calculates the correlations. Okay, so as we expected, so Y has some high correlation with the x1 and x3, but almost no correlation with the x2. Okay, so this is the basic EDA. Definitely, the EDA has the much more much more steps, like the outlier detection or the missing value um, estimation of the treat of the missing values. But here, so we're gonna just briefly look at it. Okay, then let's move to the um, actual the calculation of the coefficient and the statistical test. So in order to make the calculate the coefficient, please record the solution, analytical solution of this the multivariate linear regression case. So you may remember that the um, the solution of the beta in the matrix form. So for this matrix form, so we need to express this in the linear relationship with the matrix form. That means we have to first build the X matrix. So X matrix, it can be built by, so as a matrix, we want to make a matrix form and C bind of. So first, we want the first column should refer to the intercept of term. That is about x0, which is all ones. Okay, that is presented by repetition of 1 by n times. So this is the first column, and this C bind is in the column bind. So we bind first this one, then next is x1, and x2, and x3. So we're gonna make we have the 4 vectors in total. First is one vector, second one is x1, and x2, and x3. Four vectors. Then by combining these vectors by column-wise way, as a C bind, then finally make it as a matrix. This is X. And if you see the first 10 samples, then it's like that. The dimension of X is, it has 20 columns and 4 rows. Okay? Here, we can, according to the analytical solution, we can calculate the beta head. Right? So the first beta head is the inverse of, so inverse of X transpose times the X. So the inverse of actually that's the inverse of transpose of X times X. Here, this T function means the transpose of the X, transpose of the matrix. And another problem is this is the multiplication. This multiplication just simply means in R, this multiplication simply means the element-wise multiplication. But here, what you want to do is matrix multiplication. So matrix multiplication in R presented by percent mark and asterisk and percent. This is the matrix multiplication. Then in the analytical solution, we need to inverse it. But here there's no inverse function. in R. Instead, we can use third function. This is for the inverse. Okay. So then we also make matrix multiplication with transpose of X, and also another matrix multiplication with Y. Then this is a B hat. Okay. Then this is the coefficient. This is the estimated coefficient of the interceptor, which is true value is 3, and this is the interceptor for the coefficient of x1, of which true value is 2, and this is the coefficient of x2, the true value is 0, and this is the coefficient of the x3, of which true value is 5. So it actually estimated well. Then the estimated y hat is given by x times beta hat. This is the y hat. Okay. Here RSS, residual sum of square. Okay, which is the sum of residual means the error between observed y value y and estimated y value y hat, and and there's some of their squares. This is RSS. Okay. Then we need to calculate RSE. RSE is the root of RSS divided by n minus p minus 1. Here n is the number of samples and p is the number of variables. Here we have 3. Okay. So this is the RSE. RSE is sum of the errors. So the residual sum of residual standard errors, or the residual sum of errors, whatever. Okay, but it is calculated in this way. Okay, all right. Then here, finally, we need to calculate the standard error matrix. But this is the standard error square matrix. So this is the covariance matrix between these the coefficients. These are calculated by RSE square times, because this is just one number. Then here, inverse of transpose X and times X. This is the standard error matrix. So if we see the S input, it is like that. Okay. This is actually the standard error matrix of the coefficient for the between these betas. So each one has, so for example this one 1,1, this is the standard error, or the variance estimated variance of the the beta 0, and this one is the covariance between estimated beta 0 and beta 1, and this one 1,1 is estimated variance of the beta 1. Okay, so this one is standard error matrix. Actually, the scale of the standard error matrix, or the covariance of the these coefficients. Okay. So here actually what you want to do is we want to just capture what you need to do is we want to just capture this the diagonal part, this diagonal, because only those standard errors are actually what you need to estimate the to provide the analysis, statistical analysis for the coefficients. So let's only get these ones. In order to get the diagonal part, we're gonna use the row command for n and the column function. The rule of the, let's say, S equal is shows the result is like that. So this row function returns the row of each element. So the first row is all 1 because all elements in the first row has the row number of 1. Similarly, second row has all 2 and 3 and 4. Similarly, column function is it indicates the columns. So the first row has the value of the 1, 2, 3, 4. It's like that. So if we want to capture only the diagonal one, we just use element that of which row value is equal to of which column value. Okay, so this is the only diagonal part. So let's save it as a SE. But important thing is because this is the covariance matrix, the diagonals are all matrix, but what you need is a standard error. So we here put square root. So that's SE. Here, then, okay, so we calculate, so we have SE, standard error, okay? We have a standard error. Then also we have, the estimated beta hat. So from here, we can calculate the confidence interval. Let's say that's a CI. So you can use the whatever any kind of confidence interval, but here we focus on the 95% confidence interval. 95% of the confidence interval is between, okay, let's use the C by from the B hat minus 1.96 times SE. This is the lower side confidence interval, and the upper side confidence interval is B hat plus 1.96 times SE. Okay? And because the B hat has the vector with the 4 elements, and SE is also the vector with the 4 elements, so the calculated one is the lower part of the confidence interval of this is the beta 0 to beta 4 or beta 3. And also this one is the upper part of the confidence interval from the beta 0 to the beta 3. So by combining them as a C-byte, this CI is the kind of confidence interval matrix like this. Okay. So for the beta 0, so this is the beta 0 part. So first one is the intercept for beta 0. So it has 95% confidence interval, and from the 95% of confidence interval of the interceptor term is from 2.6 to the 3.6. And the true value 3 is definitely within this confidence interval. Similarly, confidence interval of x1 is calculated by this way, and x2 and about x3. And all of the true values are actually within this confidence interval. Then let's test whether those coefficients are actually true or not. Okay, this is so in order to that we can apply to the t statistics. So here we calculate the t value. T value is b hat minus 0 because we want to test against 0 and divide by SE. And all of the t values are like this. Then from here we can calculate the p value. Okay, p value is okay. So first of all, let's use the T0 first. Let's see the T. Okay, I'm sorry. T. Okay. T1, 1. Okay, this is a 12 point something like that. So if we want to capture the P value from the T distribution, we can use the PT function. PT function returns the value of the CDF that corresponding to the T value. So here T value is like this, and in this case the degree of freedom should be n minus p minus 1. And here again p value is 3. So this is the CDF value. and it's almost 1 because it's already very big. But actually, what we are interested, what p-value itself means, the probability that the in this t distribution, p-value means the probability that we're gonna observe the exceeding value, which is 1 minus pt, which is the very low value. Okay, and but we want the two-sided, which is the positive side, the other is the negative side. So we have to multiply 2 times of this one. Okay, and this is our p-value. So instead of using, so if we use just a t, then it refers the vectors with the 4 elements. This one. So it returns the 4 p-value. Then we store it as p. Then calculate the p-value like that. So the p-value of the the interceptor is 10 to the minus 9, which is very low. Okay, so that means there's almost no chance that the true value of this interceptor is 0, which is true because we know the truth. Similarly, there's almost no chance, the probability that the coefficient is actually 0 is this probability, so which is also very low. So there's almost no chance. However, in x2 case, the probability that we have the actual true value is true coefficient is actually 0 is this high 0.75, which is almost this is a very high probability. That means we cannot say the true coefficient is not 0. So which is also reflected the truth because true coefficient is 0. So similarly, so x3 has a very low value. So this is here finally we have estimated coefficient beta hat and estimated confidence interval I and estimated p-value p. Okay. All right. Okay, so this is all of the detailed step to calculate this one, linear regression analysis. However, all of these steps are very typical analysis, but it takes some steps. So that's why these are already have a function to provide the very simple way to provide such a linear analysis. So in order to do this one, we first combine all data with a data as a data frame. Y, x1, and x2, and x3. Okay. Then we can use the linear model function y. So it has usually has two arguments. The first argument is the model. Our model is we're gonna regress at y with. So here we use the tilde to represent the relationship. So that means we're gonna model y with x1 plus 1 plus x2 plus x3. Then those y and x1 and x2, x3 can be found from the data of the d. In this case, data is d. Okay. So this is the actual linear model. So again, this function means from the data provided data d, please model y with x1 and x2 and x3. Okay. Or simply you can use that. Okay. This that means in this data D, we have the 4 variables y and x1, x2, and x3. This that means, okay, please model y with all other values, all other variables. In this case, that is x1, x2, x3. So this comment and the previous comments are equivalent. Here, let's see f. Then it shows, okay, it returns the coefficients, which is the same with the b hat we calculated an x1 and an x2 and x3. Okay, so this is simple. Then how can it look at the statistical test result? Here we can use a summary. If we do the summary f, Here it is. Alright, so they actually shows the returns everything. So they return the residual standard error, which is we calculate as RSE, which is the same value. Okay. And here for each of the t-test, okay, for each of the coefficients, they return the p values like this. So if we compare with our p value, they are the same one, right? Because we did the same calculation. So as you see here, p-value of the interceptor of the x1 and x3, they are very significant. However, coefficient of x2 is the high p-value, means it's not significant. And the confidence interval can be obtained by confidence interval function. Then here, if we provide f, it actually calculated by default 95% of the 95% of the confidence interval, which is very similar to our calculated value. They are a little bit different because this confidence interval use um, T statistics, but here CI is we use 1.96. If you remember, this value comes from the G distribution or standard normal distribution. So that's why it is a little bit different. But fundamentally they are the same calculations. Okay, so I'm gonna stop the first program example here. So the important thing is you don't have to worry about all of the complicated things. Use simple linear comment. This one. Mm. This one gonna give you the every calculations in a simple way. Okay, so I'm gonna stop here. Okay, so thank you very much. Thank you.